the features of different types of partial differential equations and the most recent example that we considered is the example of a hyperbolic equation. So, let us continue with that. So, we could find out that x minus Ct and x plus Ct may turn out to be the two characteristic variables corresponding to this partial differential equation. And now what we will show is that it is possible to write the solution of the partial differential equation solely in terms of these characteristic variables. So, that is the canonical or general form of the solution where you write the solution in terms of the these characteristic variables. Let us give these some names, say zeta and eta. So, let us try to cast the solution in terms of these variables. So, let us do it step by step. First del phi del t. Remember, phi is a function of x and t which should be mapped to zeta and eta. So, del phi del zeta into del zeta del t plus del phi del eta into del eta del t. What is del zeta del t? That is equal to minus c, and del eta del t is plus c. Next we differentiate this once more with respect to t. So, we use the same chain rule that we used for the previous term. Again this is equal to minus c and this is equal to plus c. So, it becomes c square del square phi del zeta square plus c square del square phi del eta square. No, this is eta square minus 2c square, there are two such terms, del square phi del zeta del eta. Similarly, let us find out the derivative with respect to position. Del phi del x, what is that? This is equal to 1 and this is equal to 1. Second derivative, So, this is also equal to 1 and this is 1, hence it becomes this one. Now, we use the equation and substitute the corresponding derivatives. So, what we will get? Is equal to once we write it in this form, you can very easily simplify it because several terms in both the sides cancel. For example, these two terms cancel, these two terms cancel. So, you are left with this one, or so from here what we can conclude? It is not constant, its partial derivative with respect to zeta is equal to 0, that means it is some function of eta. So, if you integrate this once, then what is phi? It is some new function of eta which can be obtained by integrating f1 eta d eta. So, let us say that is capital F eta plus some function of zeta which is like a constant when you integrate partially with respect to eta. So, you can see that the general solution for phi can be written solely in terms of the characteristic variables. So, as if it is a function of a single variable which carries the combined spatiotemporal effect, and in terms of those two single variables you are now expressing your solution. So, it is not one single variable but two single variables because the solution has, the equation has two real characteristics. Now, if you want to get the actual solution, this is just a form of the solution, but if you are interested about the solution you must use the initial condition and the boundary condition. So, maybe initial condition at t equal to 0 phi is some fx. It is having a second order time derivative. So, you require another condition with respect to time, and that is maybe the initial, this is like the initial displacement of the string. You may also specify the initial velocity of the string. So, at t equal to 0 what about the boundary conditions? Here you can see that the boundary conditions, that is the constraints with respect to x are automatically inbuilt. that you can see. So you do not have to explicitly separately specify that again, and let us see that what is the consequence of these initial conditions, because of course how they are automatically related, x and t are related variables. So as you have different t, you have your domain of influence bounded by different values of x, and we will come across such physical examples subsequently, but let us just for the sake of completeness complete this exercise. So at t equal to 0 you have this equal to fx. So remember eta is what, x plus ct, this is x minus ct. So fx plus gx is equal to small fx, and derivative with respect to time. So first you differentiate this with respect to eta, so df d eta into del eta del t, so c into df d eta at t equal to 0. So it will become c f dash x, because eta is x plus ct, so at t equal to 0 it will become x. Remember this is this derivative is with respect to the original argument, it is not with respect to x. Then minus c g dash x is equal to gx. So from here you will get fx, if you integrate it, minus gx is equal to some 1 by c, you can just make a change of variable, plus you can put some constant of integration. So from these two equations you can now find out what is capital Fx and capital Gx.
Sir, if you are putting that limit, how can you put that constant?
No, because in this limit this is not a actual constant, this is a pseudo constant, this is a variable. So we are putting just the variable in the limit, this is not a constant limit. So if you add these two together you will get Fx is equal to small fx plus, so if you add these two it will be half of small fx plus 1 by 2c plus c1 by 2. And what is Gx? That is obtained by subtracting these two. So half of fx minus 1 by 2c minus c1 by 2. The solution is not fx plus gx but f eta plus g zeta. So let us write the solution. So that is f x plus ct plus g x minus ct. these two integrals, in one case x is replaced by x plus ct and in another case x minus ct. So, it will become from x minus ct to x plus ct. Of course, it shows that once you substitute the initial conditions, how your solution depends on the combinations of x and t. Now this gives us a mathematical feel of the solution to this problem, but it does not give us directly a physical feel of the meaning of these characteristics. So let us try to have a deeper assessment of the physical implication of the role of the characteristics. To do that, we take the example of compressible fluid dynamics. Let us say that there is a disturbance source which is moving through a fluid medium, and the disturbance source is moving through a fluid medium with some speed. So there is a speed at which the disturbance propagates, which is the sonic speed. Let us say c is equal to the sonic speed. This is the speed at which the disturbance propagates, and let us say that u is the speed of the source of disturbance. Or the speed of flow, so to say, if the flow is the source of disturbance. We know that this u by c is known as the Mach number of the flow. Let us consider a case, let us consider some examples. First example, let us consider Mach number equal to 0. So let us consider that there is a source which is located at 0, it does not move, it remains at that place. So let us consider some small time intervals, delta t, 2 delta t, 3 delta t, like that. So over a time of delta t, the source will emit a signal that will cover how much of a distance? C into delta t, and that will essentially cover such a zone which is a circle with this as the center and c delta t as the radius, because the effect is propagated in all directions. See, what is the basic difference between this and the case of an elliptic equation? In elliptic equation, the disturbance is propagating at infinite speed. Here the disturbance is propagating at a finite speed, which is the sonic speed of the characteristic of the medium. So in a time 2 delta t, it will be a radius of c into 2 delta t. So this much of additional is c into delta t. So in this way, at a particular location, it is as if generating or emitting some spherical wave fronts. So these are essentially the locus of points over which or within which this disturbance is having its effect felt, okay, but the disturbance is remaining stationary at a location. Let us consider a second example. Say Mach number less than 1. Less than 1 can be so many. So just for a special case, let us say that Mach number equal to half, that is u by c equal to half. Let us try to draw a similar type of diagram for this case. Let us say that at time t equal to 0, the source is at 0, then at a time t equal to delta t, the source will come at a point 1 which is located at a distance of u into delta t from 0, because source is moving itself at a speed of u. Similarly, in the next instant of time it moves by another distance of u delta t and so on. Now by this time what happens to the emission waves? So if you consider for example a point centered at 0, so by the time the source has come by a distance of 2u into delta t, how far the disturbance wave have propagated? C into 2 delta t, and C is equal to 2u, so 4u delta t. So taking this as a center and 4u delta t as a radius, if you draw a big circle, then that is the extent over which this wave has propagated. By the time this has come by u delta t, any source at 1, the source at 1 has emitted a wave of what extent? 2u delta t. So taking 1 as a center and 2u delta t as a radius, sorry, it is taking 0 as the center. So this is how you can have emission of different fronts. Let us consider a third example, which is the more interesting one, that is when the Mach number is greater than 1, or let us take a limiting condition when Mach number is equal to 1. So let us try to draw a similar diagram. So Mach number equal to 1 means u equal to c. So by the time this moves over u delta t and again another u delta t, the disturbance moves by the same amount. So because u and c are the same. Similarly from here it will emit u into delta t. So you can see that there is a critical condition such that the disturbance wave does not propagate beyond the point where the source is now currently located. Let us see a fourth example, when Mach number is greater than 1. Let us say an example with Mach number equal to 2, which means u equal to 2c. So, the source of disturbance propagates at a faster rate than the disturbance itself. So, by the time it has come by, the source has come by 2 u delta t, what will be the corresponding u into delta t will be the corresponding propagation of the disturbance wave front. So, by the time from 1 to 2 it has come by u delta t, the disturbance front will come by half u delta t. So, taking 1 as center and half of this as radius. So, in this way it is possible to draw an envelope of these zones of influence, and that envelope will basically come from a common tangent to these circular fronts. Of course, you can extend it on either side. So, physically your domain of dependence and your zone of influence is confined within this envelope. Not the current position of the source. I mean it is very easy to prove it. If you draw this tangent, these two common tangents, they will intersect at this one. I mean if you know that this is u by 2 and this is u, from that by geometrical construction you can easily show it. It is very trivial. So, if you have, so this is the apex of, in a 3-dimensional space it is like a cone, and the section is of course a straight line which is the generatrix of the cone. So, you get 2 straight lines as the cross section in the plane, and these 2 straight lines are nothing but the 2 characteristics of the partial differential equation. So, what basically happens is that any disturbance propagates and makes its effect felt only within this zone. Outside this zone is a sort of zone of silence. So, if there is some observer who is located outside this zone, will not feel the effect of any source of perturbation, pressure perturbation within the domain because of the movement of the source of disturbance. But when the observer just enters this zone, will definitely feel the influence. So, there is some sort of discontinuity across these. So, discontinuities of what? Discontinuities of actually the second order partial derivatives of phi. These are sort of weak discontinuities, and these are the characteristic lines across which these discontinuities are there. You can see sometimes if you have seen such physical example, if you have seen jet planes moving in the sky at a very high speed. So, these are supersonic speeds, and at those high speeds you will see that they will emit emissions which sort of will look like this particular, I mean they will have their boundary like this in a conical fashion. So, this is in compressible flow jargon is known as Mach cone. So, it is like a cone, imaginary cone, within which you have your disturbance propagation effect felt. So, question is, why do you have such discontinuities in compressible flows? or strongly compressible flows. The reason is that if you have hyperbolic equations which are valid in cases of highly compressible flows, example supersonic flows, then what happens if you have a disturbance, the disturbance propagates at a speed which is not matching with the speed of the source propagation itself. The source propagates at a very rapid rate, the disturbance cannot match with that. So disturbance tries its best to move at par with the source, but source moves at a faster rate than the disturbance. So disturbance is not able to get dissipated in that easy manner as it could have been possible for a case where the compressibility effect is negligible. When the compressibility effect is negligible, disturbance propagates at infinite speed. So automatically the effect gets dissipated throughout the medium at a very rapid rate. However, for highly compressible flows that is not possible. So the disturbance gets accumulated, so to say. So you can have the disturbance that is getting propagated of course along a certain direction which has a spatio-temporal regime associated with it, but the disturbance is propagating at a finite rate. The implication is that these are time dependent problems with significant amounts of with dissipations not that rapid or not that significant as the case that could have been possible if the propagation of disturbance was at infinite speed. So you have insignificant amount of dissipation as compared to the case with infinite speeds. So the disturbances will accumulate, and once they have accumulated too much, there may be a rapid discontinuity or a very strong discontinuity over which these disturbances are released, so to say. So you can have strong discontinuities of properties, that is you can have jumps in properties of the flow. Those do not take place across these characteristic lines, but those take place across other lines which are called as shock fronts, and the corresponding waves of propagation are called as shock waves. So since you have this accumulation of disturbances, somehow they have to be relieved, and shock waves are mechanisms by which these disturbances are relieved. So you can have possible discontinuities. One is these weak discontinuities across these characteristic lines plus strong discontinuities across the shock fronts, and once you have discontinuities, that means you have jump type of boundary conditions across these lines. So your numerical method must be able to account for such discontinuities. So that is why it is very important to know the characteristic of the equation, because if you know, then a priori you can plan for a numerical scheme that will capture these discontinuities. Otherwise you did not have special provisions in the numerical method to capture discontinuities. In fact, shock capturing is one of the very key issues in the numerical solution of the compressible flow equations wherever shock is possible, that is you have a change from a supersonic to a subsonic flow, abrupt change from a supersonic to a subsonic flow. So we have seen some examples, and these examples tell us that there is a very important role played by the finite speed of propagation of disturbance in a hyperbolic type of equation environment. Let us consider another physical example. Let us say that you have a converging nozzle you have a supply reservoir and you are maintaining a back pressure so that fluid is coming from the supply reservoir along the positive x direction. So what you are basically doing, say you are trying to increase the flow rate. So what you do, you reduce the back pressure in this chamber. Once you reduce the back pressure in this chamber, this supply reservoir will know that now I have to send more fluid at a higher rate. So it will start sending fluid at a higher mass flow rate. So this back pressure regulation is like giving a pressure perturbation or a pressure disturbance into the flow medium that propagates upstream and then gives a message that, well, now I have reduced my pressure, it is now your responsibility to respond to that and send more mass flow rate. But interestingly, that does not happen perpetually. So what happens is that if you reduce the back pressure, this mass flow rate comes, it increases, but it comes to a maximum when it comes to the sonic condition, that is the Mach number becomes equal to 1, and then you cannot increase the mass flow rate further by reducing the back pressure. So this is a well known physics in compressible flow. Question is, why does it happen? So you can explain it in a very simple manner by considering the velocity of propagation of the disturbance. So let us say that d, by symbolic notation we represent d as disturbance and f as flow. So velocity of disturbance relative to flow is velocity of disturbance minus velocity of flow. Let us say that the flow is moving with a along the positive x direction with a velocity c, then the corresponding Mach number is 1, u equal to c. So velocity of flow is plus c. Velocity of disturbance relative to the flow or what is the velocity of the disturbance? The velocity of the disturbance, so it is velocity of the disturbance is created here. The disturbance is propagating in this direction. How it is propagating? It is propagating relative to the flow. So relative to the flow, it is moving along the negative x direction with a velocity c. So velocity of the disturbance relative to the flow that means velocity of the disturbance is 0. So disturbance cannot propagate further. So you are, what you are doing is you are reducing the back pressure, but what happens is that that message is not able to get propagated. So this supply reservoir does not know that you have further reduced the back pressure. So it cannot respond to that by increasing the mass flow rate. So I mean, of course this is not a very complicated example, but if you go to more and more complicated examples you can find out similar cases. The important lesson that we learn out of it is not this example or the examples that we have considered earlier, but the moral of the example that we learned is one simple thing, that in hyperbolic type of equations you have the finite speed at which the disturbances propagate, and when the disturbances propagate at finite speed, that means what? What are these disturbances? Say pressure perturbation. So a pressure wave propagates at a finite speed. The source of disturbance on the other hand can move further ahead of that one, and that can give rise to discontinuities in the flow medium, which has to be taken into account while designing the corresponding numerical solution. Now we have seen the classifications of the partial differential equations, but a partial differential equation that contains only two variables, two independent variables, that is the generic form with which we started, but it can also have more than two independent variables. It is still a second order partial differential equation, but you can have more than two variables. So the general case can be represented in this way. Where B contains several functions, we have clubbed all together. We have seen that only highest order derivatives are important, and that is why we have just kept that as a specific term and other terms are just kept generically. So here in this case, this is a more general example than the special cases that we have considered with two variables. So here depending on the values of I and j you can have many variables, but still the highest order derivative is second order partial derivative, that is how this is still a second order partial differential equation. Now the characteristics of this equation, these depend on the eigenvalues of the coefficient matrix A. So characteristics or nature of characteristics rather depends on so how to get the eigenvalue of A? You find out determinant of A minus lambda I equal to 0. So that will give you the lambdas. If any lambda is 0 out of all the eigenvalues, if any one eigenvalue is 0, then it is a parabolic equation. If none is 0 and all lambdas are of the same sign, then it is elliptic, and if none is 0 and all but one lambda is of opposite sign. So one at least is of opposite sign than the all other lambdas, then it is hyperbolic. So let us consider an example by which we will try to illustrate this principle of classification. This is an equation relating the velocity potential for isentropic inviscid compressible flows over slender shaped bodies, that is bodies which are having a slender shape. So from that we have to identify the characteristics of the corresponding partial differential equation. So let us try to use this rule. So you have A11 this is the particular form of this one where x1 is x and x2 is y, right. So let us identify the values of the coefficients. What is A11? 1 minus m infinity square. What is A12? 0. What is A21? 0 and A22? 1. So with this understanding we will try to find out the eigenvalues of A. So it will be 1 minus m infinity square minus lambda This is the characteristic equation. So this is basically 1 minus lambda minus m infinity square 0 0 1 minus lambda. So 1 minus lambda into 1 minus lambda minus m infinity square equal to 0. So lambda equal to 1 and 1 minus m infinity square. Right. So now let us find out what are the characteristics of this equation, or what are the natures of this equation first. So here no eigenvalue is 0, right. It can be 0, one of the eigenvalues can be 0 if m infinity is equal to 1, then what happens? So one eigenvalue equal to 0 means it becomes parabolic. When m infinity is less than 1, then both are non-zero and of the same sign, so that is elliptic. So that you can see from this rule. Whereas if m infinity is greater than 1, then one of the eigenvalues is positive, another eigenvalue is negative, so it becomes hyperbolic. So you can see the same generic equation depending on the free stream Mach number can be either parabolic or elliptic or hyperbolic. That is what the important role that is being played by Mach number in compressible flows. So you cannot trivially say that this equation is parabolic, elliptic or hyperbolic without regarding to the Mach number. You have to refer to the Mach number, and based on the Mach number you have to make this conclusion that when m infinity is equal to 1 it is parabolic, when m infinity is less than 1 it is elliptic, and when m infinity is greater than 1 it is hyperbolic. Okay. Now till now we have considered classification of second order partial differential equations, but in many examples we may come across first order partial differential equations which may be applied to examples in thermofluid sciences also. Let us consider one such example and find out how do we determine the nature of such an equation. So let us consider a problem through which we will illustrate that. So let us consider a heat transfer problem. Unsteady, one dimensional, low K by rho Cp which almost tends to 0 of the flow medium. There is some heat source and u equal to u infinity approximately. So these are the assumptions corresponding to the physical problem: unsteady flow, one dimensional flow, low value of K by rho Cp, for all practical purpose it may be taken to be as good as 0, some constant heat source, and u is equal to u infinity. So with this let us try to formulate the governing equation. So let us write the most general form of the conservation equation. plus some s. So, let us consider the simplifications. So, this will have only a ddx component because it is one dimensional. This term will go away, and if you use the continuity equation together with this, you will get equation of this form. Okay, because u is equal to u infinity, one dimensional, only one x component of velocity. Let us try to find out the characteristic of this equation. T is a function of x and t. So, you can write dt as del t del x into dx plus del t into dt. So, just like what we did for a second order partial differential equation, for first order what are the variables for which we should look for the discontinuities across the characteristic? The first order partial derivatives. For second order partial differential equation we looked for discontinuities in the second order partial derivatives. For first order we should look for discontinuities in the first order partial derivatives. So, let us write those for which we are looking for the discontinuities. So, for the discontinuity to exist we must have this determinant equal to 0. So, that means 1 u infinity dt dx So, the equation of the characteristic is given by dx dt equal to u infinity. What is the nature of the PDE? Parabolic, elliptic or hyperbolic? See, never learn a subject by using magic formula. The most of the formula that we have described by this time, these formula are for second order partial differential equations. So, if you now just conclude that well I have one real characteristic, so it should be parabolic. Is it so? Let us try to assess. If you are not confident, it is possible to convert this into a second order PDE and see. Let us try to do that, because you know the classification for the second order PDE. Let us try to do that, and it is very easily that can be done. First you differentiate this partially with respect to x once. So, what you get? Sorry. S is a constant, so its any derivative will be 0. Next you differentiate the same partially with respect to t. Because it is a second order partial derivative, we are assuming it to be continuous, so does not matter whether you write t first or x first. How you can eliminate the cross derivative? Let us say this is equation 1, this is equation 2. You multiply equation 1 with u infinity and subtract from equation 2. So, equation 1 into u infinity minus equation 2. So, u infinity square Now can you tell what is the nature of the equation? Hyperbolic, right. So it is a hyperbolic equation, apparently elusive, it is giving only one characteristic, but you should not be distracted by that because it is a first order partial differential equation from which you are getting the conclusion. So it gives a fair idea to you how to find out the characteristics of different partial differential equations. So I will give you a homework exercise. Let us say that you have a system of partial differential equations, homework. So using these two equations which are coupled equations, you find out that what is the nature of the partial differential equation, parabolic, elliptic or hyperbolic. Of course it is quite easy to do, you can eliminate one of the variables either u or v. For example, you can differentiate the second equation with respect to y and from that you can eliminate v from the two and you can easily find out the characteristics by using the rules. And what I will suggest you to do is to do another homework, make a chart where you write the different features of parabolic, elliptic and hyperbolic equations for yourself, that nature of the characteristics, how many number of characteristics are there, what about the zone of influence, what about the zone of disturbance, what about the speed of propagation of disturbance. Based on these features you make a table for different types of equations, parabolic, elliptic and hyperbolic equations. So these homeworks you try to complete by the next class. So next time when we meet we will move on to our next topic. Thank you.